and good afternoon to Vincent and Johnny as well. So welcome back to episode 10 of Polly's Introduction to Computer Network this semester. And in addition to the video links we have in the announcement, there are two more items. One is actually good news. We have only one quiz during this week. Okay, but that is probably because exam is coming up tomorrow. Okay, so definitely make sure that you're on time tomorrow morning for the exam. And by the way, PA4 is not doing this Saturday. It's doing actually next Saturday. But it's just as tricky as PA3. I can see from some of you guys' submission of PA3. Pay attention, and you want to start early. All right. So this PA4 needs to work with your PA3. Okay. And you know what? Let's go ahead and start the first topic. Oh, and yeah, sure. Good afternoon, David, Rick, and Walker. So last week, what did we talk about? We talked about DNS system, isn't it? We talked about DNS. It's a application layer protocol, but it's a very important function. In fact, all the applications will need DNS. Okay, and the primary function is to find from a host name what is the exact IP address, so that I can start a socket and connect, okay, to the server. So last week, we spent quite a bit time talking about all the functions DNS provides. So hostname to IP is not just the only function DNS provides. Okay, and to store all these mappings, okay, there's a hierarchy of servers. Previously, in email, in FTP, in HTTP, we have only just one server hosting all the data. But this time in DNS, we have many servers, and they form a certain hierarchy, okay, to allow people to look up these data entries. All right, so it's extensive. So essentially, last week we talked about the functions and the architecture of the DNS system. Okay. This week, let's talk about the data side of it. Exactly what are these data being stored in these servers? Okay. They are in fact called the resource records or data record. Okay. And there are four types of these data records corresponding to the four functions we see in DNS. And here they are one by one. Let's take a closer look at the entries that DNS servers are storing there. They're called the records. Okay. Well, to be more precise, the resource records. Okay. And each look like this, a tuple of 4 elements. This is usually the host name, and this is the IP address. And this is TTL, the time these entries should stay on the server. What we haven't talked about is this type. There are actually 4 of them, not many. Let's look at them each a little bit closer. So first is type A. It's the most classical one, which says host name and the name, and IP address and the value. Essentially, this is the query, and this is the answer. Querying for this host, answer is this IP address. Second type, let's go here, the C name type. What C stands for is the canonical name. So what this does is corresponding to the second service we mentioned way earlier when we started talking about DNS. So it's doing what? Alias, the name alias service. So what it does is here, the entry there, name is the alias, the Q short one, and the value is the actual name, the canonical name, the real name. So here we have .ibm.com, cute and short, easy to memorize, but the actual name for that machine should be this, server is backup to the ibm.com. Right? So value is the canonical name. Third, let's look at this type, the MX type. So this is mail service type, and this corresponds to the third service that DNS provides. Name is a domain. Value is the mail server for that domain. So name here could be gmail.com, and the value will be what? smtp.gmail.com. Straightforward. Last type we have not yet talked about. It's actually not quite the fourth service that we mentioned about DNS providing. It's actually called the authoritative name service entry. Right? So the name there is a domain. Okay? okay? But it's not the top level domain. It's usually the second level domain. The value is the host name of the authoritative name server for that second level domain. So this is for the TLD servers to store all the authoritative name servers for all these subdomains. Right? So NS type entries are mostly in the TLD servers. All right, so 4 types of records. Okay, 3 of them corresponds to 3 of the functions, 3 of the services of DNS. That NS one is just special, okay, for someone to register a authoritative DNS server. Okay, good. Now, these records, okay, are for the clients to query. Okay, and when server receive these queries, they send replies telling, for example, for a host name, what the IP address is. For a nickname, what is the real, longer, hard to remember host name is. Okay, so we need to send messages from a client asking for a record, as well as from the servers to reply for a query. So query and reply, 2 types of messages. Next, the DNS protocols messages. So the servers exchange just the query and the reply messages to each other. They are in the same format, which is exactly what I'm showing here. There are 2 parts though. From here and up, this is the message header. From here and down, the data part, where the actual mapping, actual entries are being carried. Now let's focus on the header a bit more. The first field is called the ID. It's 16 bits long. It is used to identify a pair of query and reply. Right? Next in the flags, then you identify whether this is a query or this is a reply. So this is how server know that, okay, this reply is for a query that carries the same ID. In the flags, you might also see a certain client is saying that, can I do recursive query? In the flags, you might also see certain DNS servers saying, no, that's disable a recursive query. And coming from the authoritative DNS server, you might see this flag being turned on. The reply is authoritative. Right? There are 4 other fields in the header, these. So these are specifying the number of questions, number of answers, number of authoritative replies, number of additional informations. Now these are to serve the purpose down here in the data part, because the number of questions a DNS message can carry is variable. Now in order for the reader, receiver to know how many lines, how many records it reads, it looks up here to find out and reads up to this point and then to the next part. So that you will not be confusing a regular reply with an authoritative reply. Right? And next, let's focus a little bit more in the data part. Okay, so in the question fields, you will only see this, the name and type in a query. That's all. There's no value, there's no TTL. In the answer entries, however, then you see the full RR, the full resource records. Authority here carries records for the authoritative DNS servers. If you have also the full RRs, it's just that those RRs are the authoritative server RRs. Last is just additional information. I see rarely this part of the data being used. All right, so you see, just like many of the other messages sent by other applications, there is a header part for control purpose, and then there's data part. That's the real content being asked for. Now, so data records or resource records, RRs, are stored on the server side. Okay, although there are many physical machines on the server side. Okay, there's actually a special server called the local server in DNS service. Okay, these RRs are also stored on this local DNS server, but it's stored in a way that it's only temporary, and we call that caches. So DNS also uses caching to store these replies, okay, temporarily, much like what? The proxy server in the HTTP, if you think about it. DNS servers also cache data. And this is not the first time we hear this term caching. The first time is when we were talking about web caches, isn't it? So web cache there stores web objects, so we could reduce delay, we could save some network bandwidth. You see here, DNS, for the same purpose, also caches IP name mappings. Okay? The goal is also to reduce delay to save network bandwidth. So you see, caching is actually a very general technique for data transferring services to try to avoid repeated download. Let's go on to DNS caching. So each of these mapping will be stored at the name servers once they acquire them the first time. So these entries will be there on the server's disk for some time. So the interval is called the TTL. What it stands is time to live. So during this time, the entries stay. Once the time expires, the entry is timed out, removed, okay, from the entire disk. So an example, a local name server might store the mapping for a top-level domain server so that the local name server doesn't need to go to the root name servers a lot. Okay, again, trying to conserve the root server's capacity. Right? And the cache entries may go outdated. This is happening when the entry is not yet timed out, but the host there is already changing the IP host mapping at the authoritative DNS server. In that case, the clients worldwide will continue to get the old mapping, the out-of-date mapping, until 2 days later. This is usually the TTL of DNS mappings are set to by default. So 2 days later, the clients get the new mapping. So that's why we don't change the hostname IP mappings all that often, because during these 2 days, your customers will have trouble reaching you. So DNS caching, this is another protocol. It's defined in this RFC 2136. And by the way, the body, the community defined all these internet protocols. Okay, writing all these RFCs is called the IETF, the Internet Engineer Task Force. All right, so local DNS server, after receiving the replies from the big servers, some of these RRs get cached, stored on the local DNS server. Now, some of you might be asking this, how do these big servers on the server side get these RR entries at the first place? Okay, very good question. At the top, we have the root servers. Okay, and these root servers are just created. Okay, and you can look it up from on the web to find out exactly how many root servers there are now. Okay, so I think in the earlier slides I said 11. There might be a few more. Okay, that number is not always fixed. So once you have the root servers are there to redirect the queries to the TLD servers. Okay, so root servers will need to have these RR entries that allow the users to find the TLD servers. So when each of these TLD servers are created, okay, a top-level domain is created. Those entries will need to be registered to the root server. Similarly, TLD are there to redirect the users to the web, to the individual domains, such as google.com, such as amazon.com, such as ntu.edu.tw. So when these new domains are created, okay, these new domains will need to register their existence to the TLD DNS servers. So if we belong to something.edu or something.tw, we register to the edu TLD server, or we register to the tw TLD servers. All right, and that is exactly how the entries are being added gradually, okay, into the TLDs, and when there's TLD servers added to the root servers. And when are the entries added to the authoritative DNS servers? Well, that is when the IT department of the company, of the domain, decided that they want to create a machine and giving it a host name. They want to create an email service and giving an email service an alias to a particular server that's serving the emails. You see? Okay, so this next video, very brief, is to tell you, if we are starting a company, therefore we are creating a new domain, okay, what do? Okay, we need to register to the TLD, and we will need to also create IP, hostname IP address mappings for the web service, for the email service. Okay, so here's how you start a company and make sure that the IT connects to the IT of the company connects to the internet.
Now let's try to put our knowledge into use. So here the scenario is you need to set up your network for a startup, network utopia. All right, so two things you need to do. First, register your domain name with the DNS registrar. Now, being a .com, you talk to this company, Network Solution, who maintains the .com TLD server. Right? Second, you provide also the name and IP address mapping of the authoritative DNS server you'll be setting up. Okay, so there could be a couple of them just in case the first one failed, there's a backup. At this point, the registrar there, the Network Solution there, will try to insert two records. One is, of course, the name and IP address mapping. Second is the domain name and the host name of the authoritative server. So you see here, name to IP address is the type A, the classical one. This one here is the NS type, the authoritative type, where the TLD stores domain name and the authoritative DNS server mapping. Good. Now, back home, you need to set up a couple of these authoritative servers for sure. But inside these authoritative servers, what do you store? Well, if you want a web service, you need type A entry that keeps the name of the web server and the IP address of the web server. If you wish to have email service, then you need to set up an MX entry maintaining the mapping from the mail domain to the mail server's host name. And maybe the IP address of the mail server entry, that's another A record in the authoritative server. All right. So that's how you get your customer to see the IP address and therefore being able to visit your website.
So you see, when a new domain is created, a couple entries are registered to a company. That company then contact the TLD server and install those two RRs. And inside your company, there's an authoritative server created, and inside that authoritative DNS servers, you will create some mappings to ensure that your customers can see your website. Okay? And your employee can send emails back and forth with other people and receiving emails from other people. Okay? So that is DNS. Next, we'll start talking about, finally, the other model of architecting a application layer protocol. So previously, what we have heard so far are client-server based. Okay, so this one is the opposite, peer-to-peer. Okay, and in the introduction video, you'll see Polly saying that we'll introduce two applications. Well, you see, it depends. In case we're going smoothly today, then we'll definitely talk about two examples, two applications. If not, then we'll stop at the first example. So let me introduce peer-to-peer networking.
P2P applications. To be honest, this is one of my favorite sections in Chapter 2. All right, so P2P architecture. As opposed to the very simplistic client-server architecture where we have always-on servers, in P2P, there's no more always-on servers. Instead, we just have these arbitrary peers directly connecting to each other, communicating to each other. As you see, hey, these peers are very likely mobile end systems. So the connectivity there is intermittent, meaning loosely connected, on and off, on and off. And the IP addresses to establish physical connectivity can also change over time. So it's actually hard to maintain a fully connected session as a user moving around, for example, on NTU campus. So we'll talk about two applications. One is for file distribution. The other is for voice service, voice over internet service. So the application for file distribution is BitTorrent. And the other one is called the Skype, an internet telephone service. We're not going to talk about applications in video streaming, but there are actually quite a number of these video streaming systems in the early years that works in this peer-to-peer way. So for example, this one, Kankan from China, that's Mandarin Chinese, meaning take a look. It was a very well-established service. Okay, before we talk about all these P2P application examples, let's talk a little bit more about the benefit of shifting from the client-server paradigm to the P2P paradigm. There must be a reason why people choosing to do P2P instead of client-server. And we're going to use an example, very simple, to transmit or to distribute a file from one server to end users. Each of these users will be limited in terms of the uplink as well as downlink capacity. So look over here. This is peer I. Okay, so its uplink capacity is called UI, and downlink capacity DI. Okay, so the same fashion you see therefore for user 1, uplink bandwidth being U1, downlink bandwidth being D1, and same for user 2 and user N. The server is over here. The uplink capacity is US. Well, therefore, the downlink capacity is DS, although that we're probably not needing it in the calculation. Right? So file, one big file, size being big F. So this is the setting.
All right, so using that setting, let's see how long it's going to take to distribute a big file F to all the users using the client-server model.
Now let's calculate the time it takes to distribute the file to all end users. First, assuming client-server model, meaning server here we need to upload a copy and distribute it to each of the clients. If the uplink capacity is US, therefore the time to send one copy will be F over US. And to send N copies altogether, NF over US. And this is the term that we have here. Because the overall file distribution time will be limited by the uplink capacity and the minimum client capacity. So this is the case where the server is the bottleneck, and this is the case where a client with the minimum downlink bandwidth is the bottleneck. Now, the client carrying the minimum download rate, let's assume the value is d mean. Therefore, the download time is F over d mean. The smaller the d mean is, the longer the download time is. And therefore, you see again, in case the server is the bottleneck, the overall distribution time will be bounded by this guy. If the client is the bottleneck, the overall distribution time will be bounded by the F over d mean. Now, that's considered an N that's increasing over time. Right? Talk about the scalability of the system. The file distribution time, how does it scale with N increasing? Well, this term suggests the overall distribution time will increase linearly in N, while the minimum bandwidth for downlink might not change all that much. Okay, so potentially the overall delay if we change N is growing like this.
Now let's see if we send it peer-to-peer. Okay.
Now the same, calculating the time for file distribution, but this time in the P2P model, meaning hey, this is one of the peers, and each one of these users is also one of the peers. So they could be downloading a copy from the server, but they could also be uploading a copy for another peer. Right? Now, the server transmission time, this part now, the optimum is just to send one copy uplink. So F over US. Client there, in case it's the bottleneck, it's going to be bounded by F over d mean, which we explained. And clients overall as aggregated system, must download NF bits, and the maximum upload rate is the sum of all the uplinks for all the users plus the uplink capacity of the server. All right. So in a way, the file distribution time here for a P2P system, it's bounded by either bottleneck at the server, bottleneck at the client, or bottleneck as the system as the whole. If we want to download NF bits over this much bandwidth entirely, right? So we have the server being the bottleneck case, one of the clients being the bottleneck case, and the system overall being the bottleneck case. So NF bits that needs to be passed out, over the entire capacity, entire uplink capacity of the system. Right? So the distribution time bounded by one of these two terms. All right, now consider again if N is increasing over time, right? The scalability of the P2P modeled file distribution system. Which of the term you think is going to grow with the N? Yep, this one over here, right? It also grows linearly with the N. But if you look closer, when the number of users also increase, this term also increases. Yeah, so does this. And each peer brings service capacity. If you recall, this is also what was talked about called the self-scalability, a nice property of P2P architecture. As a peer join, right? The peer demands service, but the peer also contributes its own uplink capacity, okay, to help others to download. Okay, so this grows linearly with n, but this also increases, but not quite sure if it's growing linearly. But overall, it's going to be better than what? The linear growth. So the growth is probably more like this.
All right, so let's compare sending a big file, client server versus P2P.
Let me use a very simple scenario to contrast quantitatively the differences between client server mode and P2P mode in terms of the distribution time, right? So scenario goes as this. The client's upload rate is small u. And if we want to upload the file over this client link, f over u, and let's say that that's 1 hour. And the server uplink rate is 10u, 10 times higher than the client's uplink rate. And let's assume the downlink capacity of all the clients are just so large, much higher than the server uplink rate. Right? So bottleneck is actually here, the user uplink. Right? Now, think. Let's assume that there are 10 users. Okay? In client server mode, what is the distribution time? So let's see. 10 users, 10 copy of the file, and the uplink capacity of the server is 10u, therefore, what? F over u. And this is 1 hour. So in this case, yeah, the distribution time is 1 hour. Clear? Now, in P2P mode, let's see. We have what? 10 files, 10 copies of the files that needs to be downloaded overall. All right. And what is the total uplink capacity of the system? So user has 10u. Each client has what? 1u. So 10 of them, also 10u. Altogether, 20u. And how much is this? Half of f over u. And this is what? Half an hour. And is that right? It is right? In P2P's case, 10 users, only half an hour. Okay, so you see the growing trend, linear in client server mode, but sublinear in P2P mode. And this illustrates this characteristic of P2P system very well, self-scalability. Right? And this is the big advantage of running an internet service in the P2P architecture over the client server architecture.
All right, so you should see now why P2P. In client server mode, when the size of the users asking for a big file increases, the response time, the completion time also increase. But in P2P, as more users or more peers add in, their uplink bandwidth will be shared by the whole network. Okay, so the time is still increasing, but not increasing as fast as the client server mode. So I hope that you like such a P2P system as Poly does. Now let's start with the first example. It's called BT, short for BitTorrent. And this is a 2-minute video, a nutshell video to tell you what BT is.
First example is BitTorrent. The way the file is distributed in BitTorrent is instead of sending one big file at a time, it's divided into smaller chunks, 256 kilobytes per chunk. And the peers in a torrent actually sends and receives these file chunks. So here's to illustrate the P2P network. Okay? And each of these is a peer. Okay? And the group of peers form a torrent. Okay? And they exchange chunks of a file. Okay? So BitTorrent. Now, there's one more entity. It's called tracker. So this machine here is actually to bootstrap the process of having a new user joining or a new peer joining the torrent. So when Alice arrives, for example, what the system does is to first contact the tracker and then tracker in return, giving Alice a list of the peers. And this is the initial set of peers that Alice will connect to. Now once Alice is connected to the torrent, then Alice can try to explore other peers and then establish connections to these other peers. So tracker here is to bootstrap the initial joining process. Furthermore, about the operation of BitTorrent. A peer joining the torrent, yeah, you've heard it earlier, right? Contacting the tracker to get the initial set of peers. And those peers that are connected to Alice will be Alice's neighbor. beginning has no chunks, but over time, Alice will accumulate these chunks and eventually growing into a complete file. Now, the general operation is this. Each peer will be downloading the chunks while they are also uploading the chunks to other peers. And the peer and peers exchanging chunks, the pair could change from time to time. So they may change the peers with whom they exchange chunks. And the peers might just go away and come back in the middle of the exchange. That could be a bit disturbing. There's a special term for it called a churn. Okay? Hopefully there's less amount of these churns, but sometimes it's not really controllable. And in the end, once the peer has the entire file, for a selfish peer, he or she might just leave the P2P network entirely. For those who are more considerate, they might remain on the torrent.
All right, so that's a nutshell how BT works. Now, you see, the peers might come and go. And when the peer finish downloading a file, it's very common that they just disappear. Okay? So you see that if for a big file, these chunks, or some of the chunks in a big file, okay, the users having these rare chunks all leave the network. Then you end up having a partial file that's being distributed, circulated again, and none of the peers get the full file. Okay, that's actually not good, isn't it? So behind BitTorrent, there are these mechanisms, okay, detailed mechanisms deciding who gets to request and who gets what chunks. Okay, so this is the detail of VT.
The part that Polly finds the most interesting about BitTorrent is this. The strategy to request chunks and the strategy to send chunks. Let's talk more about the requesting strategy first. The setting is this. Given a file that many of the peers are looking for, so they'll be downloading chunks for the file. At any given point in time, because they're doing the downloading independently and they might be connecting to different neighbors, they might not know each other, so at any given point in time, different peers might hold a different subset of the chunks belonging to the file. And the way it progresses is each peer then will periodically query the neighboring peers. So asking neighbor 1, neighbor 2, and neighbor 3 for the set of chunks neighbor 1 has for that file, neighbor 2 has for the file, and the set of chunks neighbor 3 has for the file. Okay? So it's kind of an inventory check. Now once the peer receives all these inventory check reports, the peer begins to count which chunk is the rarest in the P2P network. And the peer begins to download from the rarest that he does not quite yet download yet. So that is the requesting strategy. Now if you think a little bit more about it, why rarest first? If I tell you, look back the previous slide, the issues we might run into are these, right? A peer might come and go, right? So as they move from one subnet to another subnet, it might get disconnected, the IP addresses might get changed. If it's in the middle of the download, those chunks will disappear from the P2P network. Also, right, when some peer finish downloading all the chunks for a file, and if the peer is selfish, they might just leave the network entirely. So in a P2P network, real users will all have this anxiety of not being able to find a specific chunk for a file. And that is also when BitTorrent downloading can go really, really long. It's not because there's not enough capacity, but it's more. Certain chunks are no longer there on the network. Okay, so it's actually quite important this rarest strategy is implemented on a P2P network like this. Right? And another aspect that's interesting is the sending strategy. And I love the name, tit for tat. It sounded kind of fun. Right? The way it works is also very simple. Alice here as an example peer, she will send chunks to others that are sending back to her at the highest rates. Okay, so hey, if you're generous to me, then I will be generous to you. Okay, eye for eye, tit for tat. But this simple strategy might create this problem. Other peers are not sending at the highest rate, will be choked then. These guys might not get a chance of downloading certain chunks from Alice at all. Right? This is actually not quite that good. So Alice will reevaluate the top 4 every 10 seconds. So those peers who discover that they're choked, they're not downloading any chunks, they might decide to contribute more uplink capacity. Therefore, as a result, they might get some chunks from Alice back the next round, the next 10 seconds. Okay, so this is the general strategy. Okay, share your uplink bandwidth, then I share mine. But this might not be a good thing either, because some of these peers might be very non-resourceful, meaning they have very, very low uplink capacity. As a result, they might always come up short here in the competition for the highest rate neighbors. So every 30 seconds, Alice will be very generous, okay? And not look at the sending rate coming from the neighbors, but just randomly pick one of them and start sending chunks to them. Right? So optimistically unchoke, okay, a particular peer. Now the newly chosen peer will join the top 4 and receive chunks from Alice. Right? But this is done at the lower frequency, only every 30 seconds. Right? So mostly favoring those who are contributing more bandwidth for uplink purpose, but every now and then, not bias on the uplink capacity of the peers and openly share. Okay, interesting, isn't it? And let me animate tit for tat here. So Alice here optimistically unchokes Bob. So Bob could be a newcomer into the network. Okay, Alice might randomly discover, okay, there's this guy Bob there. Alice begins to send chunks to Bob. And Bob there says, wow, thank you for all the bandwidth, all the chunks. Okay. And begin to send, also at a high rate, back to Alice. So mutual appreciation at the end. But Alice needs to be optimistic at the beginning, right? Trying to have faith, trust that whoever receiving the data would appreciate the effort. So higher upload rate finds better trading partners, okay? And so you get files faster this way.
All right, so you see that the peer asking for the chunks will look for the chunks that are the rarest first. Okay? And owners of the chunks will try to be fair, right? So for the peers who are helping more, then they offer chunks more. But there's also a little bit of random kindness there to try to allow some of the selfish peers earlier, okay, to learn that it's not good to be selfish. All right, and it's time for quiz 14. Okay, so this quiz 14 is also a little bit open. Okay, so you see that people come and go, just like you guys come and go, just like the peers on BitTorrent come and go. So are the trackers. Okay, so what are the trackers? Yeah, so this tracker is the thing a peer needs to connect to first to get the list of peers to allow them to connect to. Okay, list of peers on a torrent so that the new peer can join a torrent and start downloading a big file. Okay, so tracker is very important here to allow any peer who wants to go on a specific torrent. Okay. And the fact is that these BitTorrent trackers, okay, they come often and go away also very often. So some of the garners include supernova.org, torrent spy. So here's a screenshot of what a torrent spy look like. You can see that it's almost like a website. Okay. And there's a search bar here allowing a peer to look up the torrent you want to join. And usually a torrent is a file, okay, for example, big video file. Okay. And so you can look up like Top Gun, Top Gun's the sequel, and you will find the torrent with peers owning that video. Loki torrent, BT junkie. Okay, so from the name of these trackers, you probably, see that these people running the trackers are a little bit weird. They are. Okay, they are. Definitely not like us. Okay, not very traditional. Okay, so these are all gone. Supernova, torrent spy, BT junkie. But there's one struggling. This one is very famous. It's the Pirate Bay. Okay, I think it's still alive. Okay, one way or another. Okay, so this is what Polly has extracted from one of the news. Okay, I think back in 2015. So Pirate Bay domain, the Pirate Bay I think .net. I forgot exactly what is the last part of the domain name. It actually belongs to the Swedish government. It's probably Pirate Bay something se. Okay, so and you know what? Somebody actually bring Pirate Bay up for a lawsuit, and the Swedish court ruled that that domain needs to be suspended. Okay, and so with that domain name suspended, then of course the Pirate Bay tracker cannot be operating. Okay. But what's funny is this. Okay, this reporter is saying this, but the site likely to pop up again somewhere else. Okay, so Pirate Bay is also a tracker, and it's actually longer lasting, but longer lasting in a way that it seems dead, but get revived somewhere else. All right. So the issue here is, in order for BitTorrent, such a P2P system, to survive, you gotta have these trackers running. Okay, but you see, it's easy to kill a tracker. Okay. So now think like someone who really like these P2P systems to last longer. Okay, and Q1 asks first, hey, in order to know how you defend, you need to know how they attack. Okay, you need to know the people who are attacking these trackers. So why are these high-profile trackers shut down in the first place? Why do people want to shut down these trackers? And who are these people? Okay, so that is Q1. Q2. Now, can you redesign the way the tracker is run so that you can avoid the tracker being shut down entirely or easy? Okay, so of course you can think of ways that you run the trackers, but you can also think of ways to run the tracker. Okay, well, actually it probably seems to be the same thing. Okay, hey guys, it's an open question, so you gather the teammates, okay, and go on to the Discord channel W6 quiz 14. Okay, think about Q1 and Q2 and provide your answer in, let's see, in 5 minutes. And that might not be enough time. Okay, if that's the case, consider this quiz is also a take-home quiz. Okay, that is saying that you do have more time to think about, okay, to think through. So 5 minutes, and those, of course, come up with something you want to talk about already, can type it up on W6 quiz 14 channel. Okay, let's go. Okay, all right. So, hey, I guess the time remaining is just not long enough. I see that some of you are typing things up. It's okay. As we have only 2 minutes left, okay, what I want to say or what I want to stress is, of course, this is a take-home quiz. Feel free to think it through and then type things up. And the due time is Saturday, 6 p.m. Now, something important is this. Definitely for the exam tomorrow, go to the channel exam 1. Make sure that you read through the regulations of taking exams and make sure that you are a little bit more familiar with the process of the exam. Okay, so let me just walk it through real quick. Okay. So you see the exam accounts on the PA workstations will be available a day before the exam. In fact, they are already available. The Google Meet session and the Google Form links would also be available, but they will be available an hour before the exam. Okay. And so you want to be in the Google Meet session by 10:20 tomorrow morning. Okay. And so feel free to come 5 to 10 minutes earlier because Polly will need to check your ID, the photo ID, so that I can make sure that you are the person as what your ID says taking the exam. Okay. So that will take some time. Okay, so come at 10:20, but we'll start the exam at some time after 10:20. Okay, depending on how long it takes to check all you guys' ID. So usually something like 10 to 15 minutes. It really depends. Some of you guys will come early, so maybe the time it takes to do the ID checking is shorter than expected. Okay, so we might start also a little bit earlier. Okay, so when Polly says, let the exam begin, we start counting time. You have 90 minutes to work on the exam. Okay, and the exam is going to be in Google Form. But there is also a PDF files available so that you can actually open it up and skim through all the questions quickly. Okay, in case you want to distribute your time carefully among the questions. Okay, so you want to start from the questions that you'll be able to complete with the best time efficiency. And so you have 90 minutes. I think at some point in the middle of the exam, I would say halftime. Okay. When there's 5 minutes left, Polly will also say 5 minutes left, 1 minute left, and then Polly will do the countdown from the 10th last second, the last 10th second. Okay. And then when Polly says the time is up, you will need to stop entirely. Okay, so that includes stop working on the Google form, and hey, when I say stop, of course you stop, but make sure that you upload whatever you have on the Google form in the entire process. When I say stop, and then you hit upload, submit, that would actually give you a time that I see from the Google Form system that's later than the stop time. Okay, so typically you want to stop, okay, maybe half a minute or a minute before. So do your last submit a minute before the last time or half a minute before the last time. Okay, there's a short grace period. Okay, there's a short grace period, but know that if you submit too late, okay, there'll be points deducted. Okay, go back to the admin slides. You will see what is the proportion of points you'll be deducted. Okay. Two alerts here. So after clicking, so a minute or half a minute before you, before the time is up, you want to do the submitting because you might run into this. Yeah, a catch-us check, and this can sometimes be difficult. Okay, I think what select all the images with grass. Okay, so this one is easy. Sometimes they ask you to select images with motorcycles, but sometimes it's a little bit fuzzy. You cannot tell whether a bike is a motorcycle. So don't wait until Polly started counting down 10 seconds to do the submit. All right. And for certain questions, you might be asked to upload the file. Okay. So you can take a screenshot of what you're working on. Okay. Usually the derivation, or sometimes Polly asks you to go to a certain website and do something. Okay. So have a phone or know well how you take a screenshot. Once you get the screenshot or the photo, you can actually upload that file to the Google form. I think there's a size limit, 10 megabytes. Okay, in case it's too large, you might need to compress it a little bit. Okay, or take the photo again with the lower resolution. All right. So you'll see for tomorrow, the links will be available here. In fact, the Google Meet session is already available, but the Google Form link will be here an hour before the exam. Okay, and here's you see what your exam accounts are. It's your student ID, and all of you are assigned an initial password, which is simply s23-cn. Okay, change the password immediately and write it down somewhere. In addition to these things that Polly posted in Exam 1 channel, definitely take a closer look at the exam link from the course website. Okay, I think it's here. All right, so read through this. Okay, and I see that some of you are actually working on the old exams to get the feeling. Yeah, all these are open. And there are actually a lot more old exams that you can try to work on to get a sense. All right. With that said, I'll see you tomorrow morning for the exam, and best of the luck. Okay. So bye. Bye-bye. Oops. All right. So let me end the stream. And there we go.